This is where our coursework will actually start getting a lot of fun. We're gonna start talking about aerodynamics and how the airplane actually operates, what makes it fly, what makes it go. But in order to do that, we need to start with the basics and build our way up. So let's go over Newton's 3 laws of motion with the use of a tire.
Newton's laws of motion are foundational principles in physics that explain how objects move. The first law, also known as the law of inertia, states that objects at rest tend to stay at rest, and objects in motion tend to stay in motion unless acted upon by an external force.
Translation, that means that if the motion on something starts, it won't stop until something stops it. An airplane rolling won't stop until it hits a chalk or a tie down or a brake. It'll just keep on going, all right?
The second law deals with the concept of momentum, which is the tendency of a moving object to stay in motion. This law states that when a force is applied to an object, its momentum changes. The rate of this change is proportional to the force applied.
And we talked about this a little bit on the last video, that force is a product of mass and acceleration. If you want more acceleration, you've got to increase force or decrease mass.
The third law, often called the law of action and reaction, states that for every action, there is an equal and opposite reaction. This means that when one object exerts a force on another object, the second object exerts a force of equal magnitude but in the opposite direction. In aviation, Newton's third law can be seen in action when an aircraft's propeller pushes air backward, causing the aircraft to move forward. Now let's talk about heat. Heat is a fundamental form of energy, stemming from the conversion of other energy types. It can be described as the total kinetic energy of a substance's molecules. Various forms of energy can be transformed into heat energy. Mechanical energy, generated by methods like friction, impact, or compression. Electrical energy, converted into heat when current flows through resistance. Chemical energy, many chemical reactions convert potential energy into heat. Radiant energy, some electromagnetic waves produce heat upon absorption. Nuclear energy, energy released from atomic nuclei, as in nuclear reactions. Sun, the ultimate source of all heat energy, directly or indirectly. When gas is compressed, it becomes warm, while expanding gas cools. This relationship between heat and work is reciprocal.
Friction is a regular occurring generator of heat. Inside this hub, you'll find a bearing. This bearing is packed with grease. Now, the bearing is there to create a nice smooth operation as the aircraft goes across the ground. However, the grease is there to make sure that the heat doesn't get too hot and then it dissipates it as the bearing operates. And this is all generated from the friction between the rollers and the outside of the race.
Heat energy is quantified using 2 units, the calorie and the BTU, British thermal unit. A calorimeter is used to measure heat energy, such as the heat yield of aviation gasoline. 1 BTU of heat energy is equivalent to 778 FTLB of work. Thermal efficiency measures how effectively a heat source's potential power is converted into usable power. It is calculated by dividing the produced horsepower by the potential horsepower in the fuel.
Now, it may seem to be a little nerdy to really dig into the heating effects and the math that goes into the fuel cooling. But there's actually several engines that use fuel to cool the engine, because as the cool fuel runs over the top of the engine on its way to the combustion chamber of reciprocating or a turbine, either one, it actually grabs heat and pulls it away from the case, lowering the operating temperature of the engine. What you can't have happen is have that fuel absorb so much heat that it's useless whenever it gets to wherever it's going. Now, there's 3 ways that heat travels: conduction, convection, and radiation. Now here we have an engine on the Aztec. Cowling's off so that we can see the inner workings of it. The combustion that actually happens, that actually causes the engine to ignite and produce fire, to produce heat, it actually happens up here. But you well know that, like, as the engine runs, if you come up here while it's running and you touch the case, it's gonna be hot. You may even burn yourself. That's an example of conduction. Simultaneously, is the air around it, when the cowling's on, that you'll end up having a lot of heat build up. That's an example of convection. As the objects themselves, the jugs, get hot, they bleed heat off. That's radiation. And the way that we cool the engine, a reciprocating engine like this, is through convection, and through as the jug radiates heat through these cooling fins. Hear that? The convection happens, and the air, as the engine travels through the atmosphere, grabs the heat and moves it away, lowering the overall temperature of the engine.
Specific heat is the amount of heat required to change the temperature of a unit mass of a substance by 1 degree Celsius. Temperature scales include Celsius, Fahrenheit, and Kelvin, each with specific freezing and boiling points for water. Conversion formulas exist to convert between these scales. The Kelvin and centigrade scales are widely used in scientific work, so technical manuals often use these scales for directions and instructions. In contrast, the Fahrenheit scale, common in the United States, is more familiar to most people and is therefore used in most parts of this book. Thermal expansion and contraction occur in solids, liquids, and gases when heated. Solids generally expand when heated and contract when cooled, although to a lesser extent than liquids and gases due to their closer molecule arrangement and stronger intermolecular forces. Although the increase in length due to thermal expansion is relatively small, it can exert tremendous force if the object is constrained from expanding freely. This phenomenon must be considered when designing aircraft structures, engines, and related equipment. Now let's talk about pressure. Pressure is a fundamental concept in physics, defined as the amount of force acting on a specific area. In aviation, pressure is crucial for understanding various systems and phenomena. Standard atmospheric pressure on a standard day is equal to 14.7 psi, 29.92 inches of mercury, 760 millimeters of mercury, or 1013.2 millibars. These units are interrelated. For example, 1 psi is equal to 2.04 inches of mercury, 51.7 millimeters of mercury, or 68.9 millibars. Measuring pressure in inches of mercury involves a simple yet effective method. A test tube filled with liquid mercury is inverted and placed in an open container of mercury. Gravity tries to make the mercury run out, while atmospheric pressure pushes it back in, leading to a stable height of mercury in the test tube. Under standard atmospheric conditions, a 1 square inch column of air extending to the top of the atmosphere would weigh 14.7 pounds, similar to a 1 square inch column of mercury, 29.92 inches tall, which also weighs 14.7 pounds. In aviation, pressure readings are crucial for various instruments, such as oil pressure gauges, fuel pressure gauges, and hydraulic system pressure gauges. Understanding pressure is essential for safe and efficient operation in aviation.
An easy way to understand pressure is through this soap bottle right here. Now, if you think about the area that the soap bottle's body represents, contrasted to the very small spout. Whenever I squeeze it, you can hear the air escape. That means that all of the force that's coming here on this large area is being concentrated on this really small area, creating an accelerated, rapid rate of departure of that air. So think large force over a large area, concentrated over a small area, raises the pressure. This is exactly how brakes work. Think about the large area being the master cylinder that you push on, then the brake line that comes to the caliper is very, very, very small, and it pushes on the brake pad to slow the vehicle down, in our case, an airplane.
Now let's move on to gas laws. Gases, with their simple structure, are highly adaptable to mathematical analysis, leading to the development of the kinetic theory of gases. This theory postulates that gases consist of identical molecules behaving like minute elastic spheres, spaced relatively far apart and continuously in motion. The behavior of gases under different conditions can be explained by this theory, which forms the basis of our understanding of gas laws. One of the fundamental gas laws is Boyle's law, named after the English scientist Robert Boyle. This law states that the volume of a gas is inversely proportional to its pressure, provided the temperature remains constant. In practical terms, this means that if the pressure on a gas is increased, its volume will decrease, and vice versa. Boyle's law is crucial for various applications, such as understanding the behavior of gases in compressed air systems and determining the appropriate pressure for inflating tires. Another essential gas law is Charles's law, named after the French scientist Jacques Charles. This law states that the volume of a gas is directly proportional to its absolute temperature, provided the pressure remains constant. In simple terms, this means that as the temperature of a gas increases, its volume also increases, and vice versa. Charles's law is essential for understanding the behavior of gases in systems where temperature changes are significant, such as in air conditioning and refrigeration.
Hang around airfields long enough and you'll get to know Charles's law. We've already talked about it a little bit, but as temperature increases, the volume wants to increase in proportion with that temperature increase, given that everything else stays the same. One of the best ways to see this is actually on a fuel drum, because as the temperature increases, that volume on the inside will also want to increase.
The general gas law combines Boyle's and Charles's laws into a single expression that relates the pressure, volume, and temperature of a gas. These formulas allows us to calculate the new pressure, volume, or temperature of a gas when one of these variables changes, assuming the others remain constant. Let's see how this applied to fluid mechanics. Fluid mechanics is the branch of physics that deals with the behavior of fluids, including liquids and gases, in motion or at rest. By definition, a fluid is any substance that can flow if it is not confined or restricted. One significant difference between liquids and gases is their compressibility. Liquids tend to be incompressible, while gases are highly compressible. In the context of aviation, many fundamental principles, such as the theory of lift on a wing and the operation of hydraulic systems, can be explained and quantified using the laws of fluid mechanics. One important concept in fluid mechanics is buoyancy. When a solid body is submerged in a fluid, it experiences an upward force called buoyant force. This force is equal to the weight of the fluid displaced by the body. According to Archimedes' principle, the buoyant force exerted on a submerged body is equal to the weight of the fluid it displaces. This principle applies to all fluids, including gases. The amount of buoyant force acting on an object can be calculated using the formula buoyant force equals volume of object times density of fluid displaced. If the buoyant force is greater than the weight of the object will float. If the buoyant force is less than the weight of the object will sink. For objects that sink, their measurable weight in the submerged condition will be less than their actual weight due to the buoyant force. Aviation provides practical examples of buoyancy, such as helium-filled airships and seaplanes on floats. The size of the floats on a seaplane, for example, must be large enough to displace a weight in water equal to the airplane's weight, as specified by regulations. Fluid pressure is another important concept in fluid mechanics. The pressure exerted by a liquid on the bottom of a container is determined by the height of the liquid, not the shape of the container. This pressure is known as static pressure. When a fluid is in motion, its velocity can also contribute to pressure, known as ram pressure. The total pressure is the sum of static pressure and ram pressure. Pascal's law states that pressure applied to a fluid is transmitted equally in all directions. This law forms the basis of modern hydraulics and pneumatics. Hydraulic systems use Pascal's law to generate large output forces from small input forces, based on the ratio of piston areas. The mechanical advantage of a hydraulic system is the ratio of the output force to the input force.
For the rest of your career, you're going to have to tangle with these laws and these principles in some way, shape, form, or fashions. It doesn't matter if you're a structures guy, an avionics guy, a wrench turner, it doesn't matter. All of these laws factor in to what we're trying to do. Let's get these airplanes off the ground. Now let's talk about Bernoulli's principle.
Bernoulli's principle, a fundamental concept in fluid mechanics, explains the behavior of fluids flowing through varying cross-sectional areas, as seen in the example of a Venturi tube. A Venturi tube consists of a tube with a gradually decreasing cross-sectional area to a minimum diameter, creating a converging duct followed by a diverging duct. As fluid flows through the Venturi tube, the static pressure of the fluid decreases at points where the velocity increases, according to Bernoulli's principle. This principle states that the static pressure of a fluid decreases as its velocity increases, provided no energy is added to or taken away from the fluid. The wide section of the Venturi tube has low fluid velocity and high static pressure, while the narrow section has high velocity and low static pressure.
All right, so one of the classic examples of a Venturi tube use is a carburetor. So what the carburetor does is it takes air and puts the air through a Venturi tube to increase the speed and lower the pressure, so that way fuel can be injected into it. So here we have a Cherokee 140. We're gonna kind of go over the process. So air enters in here, goes up into the carburetor, gets squeezed into the Venturi tube, increasing its speed, lowers the air pressure. Fuel on the other side gets injected into that low pressure area. Now keep in mind that there's an engine driven fuel pump and electric fuel pump on this plane, pressurizing the fuel so that way it goes into that low pressure area with some gusto, and then from there the fuel air mixture gets piped up into the into the engine's intake manifold.
In aviation, Bernoulli's principle is crucial for understanding various systems, such as the generation of lift on an airplane wing. The curved top surface of an airplane wing acts like the converging section of a Venturi. As air flows over the curved top surface, its velocity increases and static pressure decreases, creating a pressure difference between the top and bottom surfaces of the wing. This pressure difference generates lift, allowing the airplane to fly. All of the laws concerning heat, gas, pressure, and fluids come together when we start looking at the atmosphere. Aviation's reliance on gases and their interactions with forces and pressures makes understanding the atmosphere crucial for aircraft maintenance and repair personnel. Various aspects of the Earth's atmosphere, such as its composition, temperature and pressure variations at different altitudes, and weather patterns, are carefully considered when preparing flight plans. While its composition remains relatively constant up to a certain altitude, its density decreases rapidly with height. At higher altitudes, the atmosphere becomes too thin to support respiration or combustion in conventional aircraft engines. Scientists have identified distinct layers in the atmosphere, each with unique characteristics. The troposphere, where most weather occurs, extends up to about 35,000 feet and contains about 3/4 of the atmosphere's total mass. Above it lies the stratosphere, which extends to about 60 miles and contains the ozone layer, crucial for absorbing solar radiation. The ionosphere, starting at 50 miles and extending up to 300 to 600 miles, is characterized by ionization due to solar radiation. Temperature changes in the atmosphere are non-uniform with altitude, with different layers exhibiting distinct temperature trends. For example, the temperature decreases steadily with height up to about 7 miles, then remains constant at -55°C up to about 20 miles before rising to a peak at 77°C around the 55-mile level. Atmospheric pressure, resulting from the weight of the air above, decreases with altitude. This pressure is typically measured using a barometer, with standard atmospheric pressure at sea level being 14.7 pounds per square inch. Atmospheric density also decreases with altitude, as pressure drops more rapidly than temperature.
It doesn't matter if it's an old radial engine or a modern turbine engine. They all have to breathe air, and the air in the atmosphere all affects them. Having clean air, good dense air for them to get a lot of combustion going is essential for high performance. Now, as you go and work in the fleet, you're not necessarily going to have to sit there and do the math every single time. And whenever you do have to do the math, there are charts and tables in all the engineering documentation that comes with an engine like this to help you sort through it. But we'll get to that later. For now, just remember that the atmosphere is important and something that you should pay attention to.
All of this has a significant impact on how an airplane operates in flight. Understanding the theory of flight is essential for aircraft technicians before they can effectively perform maintenance on an aircraft.
All right, now let's put all that together into the theory of flight. And let's try to make some sense of how an airplane actually works. Now, there's four fundamental forces that act on an airplane. First off, and the most obvious, is gravity. That's what keeps them on the ground. It's also the force that will come home to roost if you don't do your job right. So gravity wants to pull the airplane down, okay? Another thing that slows the airplane down is drag. Remember when being like a little kid and sticking your hand out the window of a car and feeling that air pressure push back? Well, that's drag, and drag works on the airplane as well. If you were to have, let's say, a spoiler on a wing that would stand up, the force that wing would catch and slow you down is drag, all right? So if we have gravity working in this direction and drag working in this direction, what happens in the other two directions? As the propeller spins, it creates thrust. It moves air from the front of the plane to the back of the plane and pulls the airplane forward. Now, this can happen with the jet engine. So, like, imagine if the Learjet that we have, it has a turbojet engine that's grabbing air in the front, squeezing it down, making it hot, and then shoving it out the back, pushing the plane forward. A prop pulls the plane forward in a little bit more elegant manner. And then the result of that is lift that pulls the plane up. Now, how does lift work? Where does this magical force come from? Well, it comes from Bernoulli's principle, from the wing. So as the wing cuts through the air because of the thrust, we have a equal and opposite reaction that pulls the plane up. The air underneath the wing stays at a standard temperature or standard pressure, and the air going over the top of the wing operates under a lower pressure. And that pressure differential pulls the airplane into the sky. And so all four of those have to operate in balance for the plane to be going a nice, steady flight. Thrust, if you increase thrust more than there's drag, the plane will pick up speed. Simultaneously, if you decrease thrust or increase drag, let's say you throw a drag chute like we have on the Lear out the back, it'll pull the plane and make it go slower. Simultaneously, now gravity is more or less consistent. Technically, the farther away from the center of the Earth you get, the less gravity gets, but it's minuscule and not really relevant. But gravity stays more or less standard, static. But lift can decrease. So if thrust decreases, lift decreases because the plane's not going through the air as fast. And so as that happens, gravity, which is going to be constant, takes over and pulls the plane back down. Now that is the basics of aerodynamics. Everything else gets extrapolated from those four principles. And we'll see those as we go forward.
Airfoils are fundamental to understanding how aircraft generate lift and propulsion. An airfoil is essentially any device that, by either applying Bernoulli's principles or Newton's laws, generates a force when air flows over its surface. This principle applies to various components of aircraft, such as the wings of airplanes, propeller blades, helicopter rotor blades, or the fan blades of turbofan engines. In the case of helicopters, these rotating blades are often referred to as rotary wings, highlighting their dual role in creating lift and thrust. In aerodynamics, every airfoil, whether it's a wing, propeller blade, or rotor blade, possesses two defining features: camber and chord lines. Camber refers to the curvature present on the top and bottom surfaces of an airfoil. Typically, the top surface has a more pronounced camber, while the bottom surface is often relatively flat. However, in symmetrical airfoils, the camber is the same on the top and bottom. The camber's role is crucial in generating lift. The increased curvature on the top surface causes the air to flow faster, resulting in decreased static pressure. In contrast, the bottom surface, with its flatter profile, has less velocity and higher static pressure. This pressure difference between the top and bottom surfaces of the wing is what generates lift. The chord line is an imaginary straight line that runs from the airfoil's leading edge to its trailing edge. The angle between the chord line and the airplane's longitudinal axis is known as the angle of incidence. This angle plays a significant role in determining the aerodynamic characteristics of the airfoil and, consequently, the aircraft's performance. Understanding and manipulating these features are essential in aircraft design and aerodynamic analysis. The relative wind plays a crucial role in aircraft aerodynamics, representing the airflow's direction relative to the aircraft's wing. In normal flight conditions, the relative wind is opposite to the aircraft's flight path. For instance, if the aircraft is moving forward, the relative wind is backward relative to the aircraft. In aviation, understanding the concept of relative wind is fundamental to grasp how aircraft generate lift. The relative wind is the airflow's direction relative to the aircraft's wing. In normal flight, this wind blows in the opposite direction to the aircraft's flight path. For example, if the aircraft is moving forward, the relative wind is blowing backward relative to the aircraft. The angle of attack is another crucial factor. It's the angle between the airfoil's chord line and the relative wind. As the angle of attack increases, so does the lift generated by the wing. However, if the angle of attack becomes too steep, the airflow can separate from the wing, leading to a decrease in lift. This condition is known as a stall, which can be dangerous if not managed properly.
This sensor on the side of the Lear is called an angle of attack sensor. As the plane pitches, this wedge grabs the air and moves up and down, allowing the pilot to know exactly what the angle of attack is of the plane.
Aircraft wings come in various shapes, known as planforms. Common shapes include rectangular wings, which are typical on small general aviation airplanes, and elliptical or tapered wings. Swept-back wings are common on airplanes that operate at high subsonic speeds, while delta wings are used for supersonic flight.
Two numbers that you need to remember, or two measurements rather, you need to remember about wings: chord and span. So chord is from the front to the back of the wing, from leading edge to trailing edge of the wing. And then span is obviously just from the tip to tip, the wing span, how big it is. Now, when we compare those two numbers, we get a figure called the aspect ratio. Now, aspect ratio of a wing tells us a lot about that wing. It'll tell us that if the aspect ratio is very, very high, if it has a short chord but a very long, wide span, well, generally it's really good at producing lift under low power conditions.
This design is often found on gliders. Many aircraft have a greater angle of incidence at the root of the wing than at the tip, known as washout. This design feature helps maintain aileron control during the initial stages of a wing stall by causing the inboard part of the wing to stall before the outboard part.
Wing design is a fascinating thing to study, and if you learn your wings, you can almost walk up to a plane and know exactly what it's meant for. High camber, beefy, rectangular wings are really good for stability and for performance at low airspeeds, dropping the speed in which the airplane can operate down very, very low. So you'll see a lot of that on like bush aircraft and aircraft that are meant to carry a lot of weight and be able to take off in a small area and land in a small area. However, you look at an F-16 wing, it's the exact opposite. It's very, very thin. It's made for like very dynamic stability, so that way the pilot can juke and jive and make it operate. And it also operates at an extremely high speed. It also means that its landing speed is also very, very high, which means its landing length is also very, very low or very, very long. Not every wing is perfect for every situation. A delta wing that's swept really far back performs very, very well at high speeds, but at low speeds, it almost wants to fall out of the sky. You have to have the airspeed over the wing for it to do what it's supposed to do. There's been other attempts over the past years to try to create wings that can swivel and hinge and take advantage of the different designs at different airspeeds. So if we think about the F-14 Tomcat that Top Gun, the original Top Gun was filmed, that plane can swing its wings out for carrier landings to reduce the length of rollout on landing and lower the speed. But at supersonic, they can tuck their wings back and go super duper fast. So knowing wings will absolutely help you in the future as you continue on your aviation career.
Boundary layer airflow plays a crucial role in how aircraft wings perform. This thin layer of air adheres to the wing's surface due to air viscosity. As the wing moves forward, the boundary layer starts off as a smooth, laminar flow over the streamlined airfoil shape. However, as the air travels toward the center of the wing, it loses speed due to skin friction, thickens, and becomes turbulent, known as the turbulent layer. This transition from laminar to turbulent is called the transition point. High angles of attack or increased speed can move this transition point forward, leading to increased drag due to skin friction. As the boundary layer thickens and turbulence increases, there comes a point where the airflow breaks away from the wing's surface, causing a stall.
Now, our aircraft's flying along, and it gets into a situation that's not generating enough lift to stay in the air, and what it wants to do is stall like that. And the reason why that happens is that the air that's passing over or going under the bottom of the wing is at a certain pressure level, say standard pressure today, 29.92. The wing that's going over the top is going faster, lowering its pressure, causing the wing to produce lift. Now, if you slow that air down for any reason, then all of a sudden it can't produce as much lift and the plane struggles to stay in the air. So the icing conditions, as you fly along and ice gets built up on that wing, it won't feel like all of a sudden like a stall like that most of the time, unless it's really, really bad. But what will end up happening is that you'll notice that you're sinking because you're just not producing enough lift. And that's why it's important to keep those wings super clean, is to try to produce as much lift as it possibly can, be as efficient as it possibly can. Now, there are some devices that will actually help an aircraft stay aloft even at slow air speeds or adverse flight conditions or whatever. One of those is a vortex generator, or you'll hear them called VGs. And there's even kits out there to upgrade planes to put VGs on their wings. And I've done some of those. It's pretty interesting. You would think that it's like some sort of crazy sheet metal mod, but really a VG looks like a post-it note that has been the sides have been turned up on it, kind of something sort of like that. All right, and you would mix a certain adhesive. You would go through, you take a template, and you lay it on the leading edge of the wing, and you mark where the center line of the VGs are going to be at. And you go through there and you glue all these little sheet metal folds on there. And what that does is as the wing produces, or as the air starts to go over the top of the wing and slow down, it prevents that boundary layer separation and keeps the boundary layer sucked into the wing by creating like little vortexes that suck the air back down. It's real popular on certain turboprops. You'll see a lot of King Airs have VGs. It's also really popular on bush planes. So like right now, the short takeoff and landing world is really taking off and becoming very, very popular. And one of the popular mods you'll see people do is do a vortex generator kit, STC. And that's what those are. Another one you'll see real popular, especially on like de Havilland aircraft, is the one that kind of comes to mind, Beaver, Otter, is stall fences. So a stall fence, all it is if you were to take your aircraft and think about the way that a stall generally progresses. Most of them they are made to progress from the root. So from here, and coffee pot's going. So from here and then progressing out this way to try to save the aileron from being from stalling out, so that way it can still control the airplane. And so a stall fence is just a metal fence. It's like a metal bar that runs down the middle of the plane or the middle of the wing, and as the stall progresses, it gets hung up and can't hop that fence. That little bit of a hang up allows the plane to fly slower and slower and slower, still producing lift. So very innovative, very simple. Most of these are actually very, very simple approaches to solve very, very complex aerodynamic problems. The one, and we'll look at one here in just a second on the Lear, is a stall strip. And all that effectively does is it actually spoils the lift coming over the wing, so that way the pilot understands, hey, look, I'm getting into a stall condition, and I can start to feel the buffeting, which is an important thing to cover too. Is that as the plane goes to stall, it doesn't just go without any warning. You'll start to feel the controls get mushy, and you're like, man, what is going on here? And then it'll start to buffet, and then it kicks over. Those stall strips are made to induce that buffeting artificially and early, so that way you start to like say, hey man, like, you know, what's going on here, and then start to nose the plane over to try to pick that air back up. It was a great way to get what is known as haptic feedback, the you know, stall shaking, some sort of physical shaking on the column before they had stall shakers that you see on modern aircraft. But that's it. That concludes our talk on heat, physics, aerodynamics, and these are all the basics. So save this video, watch it multiple times. There's a lot here, and it's even condensed. There are certain things that we reallocated to other videos because there's just so much. Like you really need to read the 8083 and know this backwards and forwards and in your sleep, because whenever you go to analyze a problem or a repair, these are things that need to be instinctual, so that way you just like understand, like, okay, yeah, this is what's going. And you'll get there. The more you work on these, the more you have to like, especially doing any kind of aircraft mods, you'll definitely get to the point where these become second nature. So stick with it.